Hello everyone, my name is Gustavo, and in this presentation we'll be talking about our capstone project, Aerotrace. Our goal for Aerotrace is to develop a tool that can make any disc golf trackable via GPS. This enhanced disc golf disc would be able to give the user real-time statistics regarding both the game as well as the summarized stats that the user can look back on. The three main statistics that we were going for in this project was location, velocity, and altitude. Our final project consisted of a successfully implemented circuit that can collect data from the GPS, parse it, and properly deliver it to the user via a Bluetooth app that is developed and designed by our team of engineers. This app can successfully present all these statistics that it has gathered in a clean and user-friendly interface in order to maximize and enhance every disc golf game experience. Not only were we able to gather the location, velocity, and altitude of our disc, but we're also able to incorporate the track angle of the throw. Now, before we begin, I should probably mention a little bit about what disc golf is and how our project plays a factor in disc golf. Now, disc golf is a sport where, similar to golf, the player wants to put their disc inside of the basket with the least amount of throws. The sport is commonly played without the ability to achieve reliable game statistics, both in the amateur and professional settings. Now, Aerotrace wants to change this by making a reasonably priced electronic device that will be able to help the user track their data and performance on a course in real time of each individual throw. This is our project schedule. It consists of the full semester starting in January and ending in May. We incorporated both our milestones, where milestone 2 is including the final testing and implementation of our circuit. Now I'll quickly go over the roles for this project. Ronald was in charge of mostly the BLE systems and developing an MCU and programming it, along with some GPS implementation. Preston was also in charge of the front end and some soldering, and he also helped out on the BLE system. Arturo was in charge of the power supply and a lot of the PCB design, and I kind of played everywhere, but mostly part of the GPS, power supply, and the disc design.
For our project, luckily the budget was under budget the entire time. We were able to only need the initial $1,200 that was allocated to us. Originally, we had expected a cost of around $570, but as we progressed through the project, we figured out that we ordered incorrect parts and had to order more. We also wanted to fabricate a minimum of 4 PCBs with all working components on the disc. This made the initial expenditure increase to a total cost of around $870.03, leaving about $330 to spare. The main source of this increase came from the power supply, the GPS, and MCU. During testing, we figured out that our MCU that we ordered was fried and had to order more throughout the final weeks. We also ordered a decent number of batteries and GPSs just in case something hindered the circuit we created. The case and disc were free, as well as the PCB fabrication, as we in-housed this through the shop and used the school's equipment to make our project.
So this is the block diagram of our project, and it allows you to see how each component interacts with each other and how it all comes together. So let's first begin by talking about our GPS. We chose the Aerotrace Ultimate GPS, and the main reason was its size and its capabilities of sending data to our MCU. We first tested the capabilities of our GPS by placing it with the MCU. We basically connected the MCU and the GPS to the computer, and we went outside and did a lot of field testing to check how accurate the GPS really was able to be. So again, this is just a closer look as to how we had the MCU and the GPS set up. Basically have 2 pins, one for receive and transmit from our MCU, and we have a power, so a positive and a ground pin connected to our MCU to our GPS. And that basically powered the GPS, and we're able to also provide information from the GPS to MCU via those pins there. So using CircuitPython, we're able to program our MCU and retrieve this data from our GPS. At first, we had a output signal that was just in our terminal, but later on, we were able to parse it slightly to get a more accurate data, as you can see here on the picture on the left. And it's a lot easier to read that, but it spit out all sorts of information, including the number of satellites, how well it fixed, longitude, latitude, and things of that nature. Not only that, but we went ahead and we checked how accurate the GPS was, and as it stated in the data sheet, it would be at least 5 meters of accuracy. It did indeed provide that because it pinpointed exactly our latitude, longitude accurately to where we were present when we were performing field testing.
As referenced previously, our MCU that communicates with the GPS in order to properly retrieve data from the device is a Xiao C Studio NRF52840. We chose this MCU for its small form factor as well as its onboard Bluetooth low energy antenna. The first iteration of our BLE program would allow users to connect to the MCU. Then it would ensure that the GPS has a fix before transmitting the data that the GPS had collected. This was a great proof of concept, but the only problem was that there was no way of reconnecting to the device or logging data when the device is disconnected from the phone. The second iteration of our program would ensure that upon disconnect, data from the GPS would be stored in a temporary array, and the BLE program would restart back to the advertising process to get reconnected to a phone. Lastly, our final iteration would ensure that the saved data within the temporary array would upload all the unset data that was collected by the MCU, and then properly start feeding back real-time data.
The power supply and charging station went through a multitude of revisions. Shown here is the original schematic layout of our circuit that charged the 3.7 volt batteries. Next, here's the PCB layout, with it also encasing the holders for the batteries. This also shows the power and signal lines for the MCU and GPS as well. This original drawing was made in respect to allowing the maximal current draw from the batteries, which in turn allowed for 2.5 hours of charge every full charge. That is why the original PCB contains 2 charging terminals for both batteries, as well as the batteries going into the MCU and GPS. The 24.5mm battery was rated at a max dissipation rate of 40 milliamp hours, which covered the GPS's requirements, and the 35mm battery covered the MCU's requirement of 200 milliamp hours if it was utilizing the chip and its BLE to its full capacity. This 3D model of the PCB was created using KiCad, which is the software we use for the schematic drawings, the PCB drawings, and the Gerber files as well. These next slides show some revisions made to the PCB to compact the board more. We decided to get rid of the 24.5mm battery, as shown in this slide, which made the board a lot smaller, but as a result, we could not utilize the MCU to its full capacity, or the battery couldn't supply the proper power to both the MCU and GPS. This next slide shows our final PCB that we ended up using. We went through 11 iterations for the PCB in total, with each revision optimizing the weight and size of the PCB as we progressed through the creation. To explain the PCB, in the bottom left part of the circle, which contains the USB-C input that has a voltage rating of 5 volts DC. This gets put into the charging controller, from which a current is set using iSet from the charging controller's datasheet. In our case, we had an RSet value of 2.1 kiloohms, which produced an iSet value of approximately 214 milliamps. This is in the threshold to charge the battery, so we felt like this was okay, even though it was a little under what the proper charging current was supposed to be. The output of the charging controller was put into the positive terminal for the battery, where the positive terminal contains a trace that goes to an on-off switch. When on, the battery powers the MCU, which in turn powers the GPS. When off, the switch creates an open circuit with the battery, meaning no current is passed through and no power is being provided to the MCU and GPS. This slide is a front and back photo of what the PCB ended up looking like physically, and from our testing, the battery provided proper power and charge. It fully charged within 2 to 3 hours and lasted for approximately 2 hours in total. This video here contains a time lapse of the battery getting charged to its full capacity.
As far as casing went, I knew I needed something that would be small and that would be able to fit inside the disc. At first, I designed this prototype in hopes that it would be able to fit the disc and close our PCB so that anytime we threw our disc, our PCB would not be bothered by any foreign objects. So after modeling it, I went ahead and printed it, and this is the monstrosity we get. It is too large, and it occupies too much space in the disk. But it does close, which is a good step. So after a little bit of brainstorming, we decided that it would actually be better if we just 3D printed the disk as well as 3D printing the threads. And we decided to implement the threads straight into the disk so that when you put the lid on, it would be a slick and slim format where our PCB would just sit right in the middle. And this is the design that we decided to go with overall. And I went ahead and printed it, and this is what it looks like. Finally, we decided to go with this design, implemented a little logo, and made the cap as small as we possibly could so that it would be able to fit our PCB without a lot of wiggle room. So after a lot of suffering, we proceeded to do a couple of final adjustments like the threads and make the case as slim and as light as possible so that we could maximize our weight. And finally, this is the final design that we came up with. Once 3D printed, painted, and finished, with the PCB inside, we get a total of 174 grams with the disc on the left, and to our right is the actual disc golf disc weighing at roughly 164 grams. So this is a big deal because we hit our mark of being below 200 grams. And not only that, but we're just shy of 10 grams of being the actual weight of a disc golf.
Finally, for the front end, here is a drawing I drew towards the beginning of the semester, outlining what I wanted the app to look like and all the things I wanted to display. So that would be, it would have a marker like on the map tracking where the disc has been, and then it'll tell you the speed of the disc, the heading, altitude, and then the total distance with the ability to reset it to clear the map and to clear all the data. This is a video of us once we got the front end up and running a little bit more. We have the navigation tabs working, which was giving us a little bit of pain towards the beginning of the semester, as well as you can see our map is working now here. And this is an older version of our Bluetooth screen where you can scan for the Bluetooth devices and then you'll be able to connect it from there. We've since changed the UI a little bit, but it effectively remains the same. This is a picture of once we got the marker working on the map, so it would constantly display the location of the disc, as well as then receive the speed, altitude, and the heading from the MCU as well. Here's a screenshot of once we were further along, we worked on the polyline feature, so we would draw a line of where the disc has been, and then that would obviously get reset when you press the reset button. Here is Ron driving around the block, and yeah, it worked out great.
Lastly, here is our final demonstration video. Please enjoy.
Today is a beautiful day out here for you to be disc golfing, so we'll be demoing our project Aerotrace. So here's just a plain disc golf. As you can see, we've made a disc that is able to calculate all sorts of statistics for your disc golf throw. So first I'm just going to give you a normal, usually what a throw looks like, and then we'll go right on ahead and look at what our Aerotrace app can perform. So come along. So here's just a normal, simple disc golf throw, and let me show you how it's done. As you can see, I threw the disc, but what's my speed? What's my throw? Well, worry no more. Aerotrace is here to help.
To use Aerotrace, all you have to do is turn the switch on, and then the GPS will begin searching for a satellite. We'll then insert it into the disc and screw the lid on. From here, we can just go on our app and try and connect to the MCU, and it should be connecting. Alright, as we can see here, it's connecting, but since the light is still blinking, it is still looking for satellites. Alright, the satellite has been found, as you can see by the numbers popping up on the screen. So now I will demonstrate with the throw. Alright, as you can see, we threw it away from the GPS range, So we'll need to go over there to reconnect to retrieve our data. And as we approach the disk, we simply reconnect, and as you can see, our data will load in with the line on our throw.
Some future implementations we want to work on are to improve the user interface for easier use of tracking, adding a homepage to better track the throw at each collected point, ensuring the Python script within the MCU does a better job in handling Bluetooth disconnects, decreasing the time it takes to connect to the Bluetooth device, adding more data such as horizontal dilution, number of satellites, rotations per second, and more. Lastly, we want to increase the data collection from 8 to 10 Hz so that the application has more data to utilize.
Before we wrap up, I want to talk about some of the things that we're proud of as far as what we've done this semester. The big one would be that our Aerotrace device fits within the desired weight. Throughout this whole semester, I was making a big point where most disc golf discs are within the 150 to 190 gram range. So I was telling the team that as long as we can fit it below 200 grams, I think that it'd be great. And we managed to get it well below that with a weight of around 180 grams, depending on the disc. And yeah, the disc, it's not too large with the PCB, which is another thing I was also worried about, especially with some of our earlier renditions of the casing on it. One of the things I'm really proud of is, I was worried that the disc wouldn't fly that great, having all of its weight distributed to the center. But as you can see from our video, it actually flew great. That was one of the things I was very impressed with, and I couldn't have asked for a better result, in all honesty. And then finally, we were able to get all the data points we originally wanted. For a while, I wasn't sure if we'd be able to get the polyline, where it would map the locations that the disk has been, but we managed to get it working, and as well as the speed and all the other ones, which I'm very happy about that, because I was worried we were going to have to make some sacrifices.
And with that, we conclude our final presentation for our senior capstone, Aerotrace. Thanks for watching.